Now there are 76 of you now in the class. In these online sessions, we are supposed to have 91. Okay. Now, I have shared with you this, I think, the last week's lectures before we end the last week lectures on these are the problems that you are expected to be able to solve. These are statically determinate beams. And shown here, those forces in red colors, they are reaction forces at the support. And we have seen how to use equilibrium equation to solve them, including problems with hinges. Now, if we separate this beam, this continuous beam at the hinges there, we get the green color forces, which are the internal forces. So I separate that into color to get to emphasize to you the internal forces. The green one appears only when you cut the beams or the frames at the particular sections. In this case, we cut at the hinges there. Then only that forces appear. So when you cut a beam or the frame, remember you must remember to indicate internal forces that will happen at the location where you cut. At the hinges, there are only two. There are only two internal forces, but if you cut at any other place, there will be three. And some of them will become zero, but in general, there will be three. So here, internal forces, if we need to analyze this, then we can just analyze it easily. Like what? If you want to analyze Bx and By, so you can take this part of the free body diagram, use the equilibrium equation, then you can get Bx 0, By at 50. The same thing if you want to analyze for Ex and Ey, you can make use of this free body diagram. Then you will get Ex 0 and Ey third. Okay. So these are internal forces. If we are asked to evaluate what is the internal forces acting at the pin, so you have to cut at the location of the pin. So when you want to get internal forces, you have to cut. Internal forces acting on a member of a planar structures, 2D structures, there will be three. And when we want to look at internal forces, so I shown here, these are the reaction forces at the support that you separate. When you separate this beam from the support, in the free body diagram, you need to indicate the support reaction. These are external. We call it external to the beam or to the frame. And normally, when we want to represent sections, we use this symbol, dotted line here, XX. We cut through here. Then we separate the problems into two parts, one on the left-hand side of the cut and the other one on the right-hand side of the cut. And when you cut a sections, remember class, remember, you must always indicate internal forces there. There are three, but in this case, the actual force here is very clear. Here is 0, so it becomes 0. But it's not necessarily all the time 0, but for beam, normally there are 0 actual force, the internal force, unless you have a load which is acting in the x direction of the axis of the member. Then in certain part, you get axial force. So the green color here, these are internal forces. So shear force, these are the shear force and bending moment diagram, bending moment. So these are the forces which are unknown that we need to do analysis to determine them. So the meaning of these internal forces is the one on this side, left-hand side of this cut section represent the actions on the right-hand side, on the left-hand side. And this one represent the action on the left-hand side, on the right-hand side. So this represent the action on the other side of the sections where you cut them. So internal forces that is important for beams and frames, these are shear force, bending moment, beams, and frame. There will be additional one which is the axial force. And this one, you remember, you can recall EAS152, you have learned this. Okay? And this shear force and bending moment, why they are important starting from year 1, year 2, because these are important for the design of beams and also for the design of frame. So now let's recall a little bit what you have learned before when you calculate shear force and bending moment. So here in general, we want to make sure that you're aware that there are 3 internal forces, so we also include axial force. But normally in beam, axial force is 0 unless we have load which is acting in the directions of the axis of the beam. So normally when we want to determine internal forces, the first step that we have to do is we have to calculate. That is first step. That is the first step. So here we can get the reaction force easily by taking moment at point B, then you get A. After that, by using equilibrium equation of forces in y direction, you will get the other reaction forces. Here it is using the method of ratio in order to get the reaction forces AY and BY, and AX is equal to 0. Now, to get internal forces, class, you must cut at the place where the internal forces are needed. So we are asked to calculate internal forces at D here. Where is D? D is 2 meters from C or 8 meters from A. So it is important to know where the section is, where you are required to know the internal forces. So you have learned this, you cut the beam at the sections where the internal forces are required. Then when you cut the beam at the particular sections, the beam will be separated into 2 parts. So you can use the sections free body diagram. You draw free body diagram for the parts on the left hand side of the cut or on the right hand side of the cut. Either one can be used. But there are one important things that you need to take note of, so that whenever which side of the cut section that you use, you get consistent results. So that is one point that you have to pay attention to, which I will emphasize. So you can use either parts to get the internal forces, axial force Q, shear force S, and bending moment M. So we use this symbol QSM. Sometimes we can use a Q also, other symbols, and some books might use other symbols, and then sometimes we might use other symbols in these lectures. But the important thing is to know that Q is acting in the axial directions of the beam, as shown in this diagram here. S is acting perpendicular to the axis of the beam, and bending moment, is a bending moment, is a moment which is acting at these particular sections. And we have set the directions that we want to use consistently. So Q, if we cut here, use the left hand side, Q is pointing like this, S is pointing downwards, M is counterclockwise. So this one we will come back, we will come to this part later on. So it is important to indicate whenever you have cut through a section, there are 3 internal forces, and indicate them in the direction that we agree on. Okay, so that the calculations result become consistent. So the next is, after you cut this, if you use a free body diagram, you cut here, you use a free body diagram on this part here. So this is what you get. X is this direction, Y is this direction, so indicate the internal force. Then the next part is apply equilibrium equations. So apply equilibrium equations. Q is in X direction, so from this you get Q. S is in Y direction, so from this you get S. And M to take moment. So take moment, in principle, you can take moment at any point. Take moment D, C, A, or any other points here within the plane of the structures. But it is easier if you take moment at the cut section here. so that you do not need to consider moment caused by S. So sometimes in the calculations, if you get S wrongly, then it will affect the bending moment as well. So if you take moment at the cut section here, then S does not cause any moment. So even if you make mistake in shear force, at least your bending moment is still correct, provided your moment equation is written down correctly. So we solve this, then we get shear force 0, which is normally happen in beam class. S is negative 30, so negative 30 by now, if you get a force, negative values, meaning that the direction that you assume in the free body diagram is wrong. So here, instead of going down, shear is actually acting upward here. So bending moment 60, so it follows the directions that we assume. So this is the steps involved. Now, you can always use the section on the right-hand side of the cut. So just to complete adding the explanation here, either side you can use. So if I use the free body diagram on the right-hand side of the cut, so I indicate here, I use the right-hand side. Just now we use this part. Now we use this part. So now, if you draw the free body diagram, this is what we get. So we indicate again, class, I emphasize again, when you cut any section in the 2D structures, you will have 3 internal forces: axial force, shear force, and bending moment. So if you pay attention now, the directions that we indicate here is a little bit different from the direction that we indicate if we use the part on the left-hand side of the cut. So we will come to this later on, how to decide the directions of the Q, S, and M. So apply the equilibrium equation again, you will get the same answer if you use a consistent way of indicating the directions of Q, S, and M, whether you are using the right-hand side of the cut or the left-hand side of the cut. So this is just revisions of what you have studied. First, you draw free body diagram, then you get the reaction forces, then you look at the section where you want to determine the internal forces, in this case axial force, shear force, or bending moment. Then you make use of the 3 equilibrium equations, then you can get axial force, shear force, and bending moment, including the directions, the proper direction of the corresponding internal force. So here, if we put them two together, so if you want to determine internal, here in the previous example here, we want to get the internal forces at the cut section DD here. So we need to know what is DD here, these sections. We use this symbol to indicate these sections. So if you cut this, you get 2 parts, one on the left-hand side of the cut, one on the right-hand side of the cut. So we have applied the 3 equilibrium equations to determine Q, S, and M. Q, S, and M, we get the same set of values, regardless of you're using this side or you're using the right-hand portions of the cut sections. Okay, so that shows to you that you can use which side. So which side we want to use, it depends on us, and we use the side, we use a free body diagram where the number of forces involved is less. So our equilibrium equations, the forces involved will be less, and then the tendency to make mistake also will be less. Okay, so if you compare these and these, so the number of forces that you need to consider in equilibrium equations will be less here. So it will be easier to use these right-hand portions of the cut sections to get the Q, S, and M. But it totally depends on us which part we want to use. Okay. Now, the same results are obtained only if we use the consistent, what we call the positive direction for Q, positive direction for S, and positive direction for M. Here, if you pay attention to this section, this free body diagram and this free body diagram, you see Q is pointing like this, here is pointing like this, S is pointing down, this is pointing up. M is pointing like this, counterclockwise. Here is rotating clockwise. So this how to indicate the positive direction that we assume first in the process of getting the internal forces is very important to make sure that the same set of results are obtained. If you do not follow this, then you might get S here positive, here S here negative, which is not correct. So this is what we call sign conventions that I think you have also been exposed to. Yeah, sign convention. Sign convention is an agreement on the positive directions of axial force, shear force, and bending moment at the cut sections. So in this diagram here, we cut through this portion here, and we show this particular portion that we cut from this beam. Then further in this particular part, we further separate this section here into two portions, one on the left, one on the right. And when you cut here, then remember internal forces appear. Internal forces appear and should be indicated on the free body diagram. So I have Q here, S here, M, Q, S, and M. And this is the positive directions of Q, S, and M if we look at the free body diagram on the left-hand side of the cut, and this is a positive directions of the Q, S, and M if we are considering the right-hand side of the cut sections. So this is the sign conventions that we agree on. So we agreed, it's like we have an agreement. So let's consider this as the positive directions. The left-hand side, like this, the right-hand side, like this. So it is very important for us to have this sign convention, because if we follow these sign conventions, then remember we can use either this part or this part of the cut section to determine the internal forces. If we follow these sign conventions, then we are going to get the same set of results, including positive, negative sign of the Q, S, and M. Yeah, regardless of which side of the section is considered for computing the internal forces. Sign convention is important, is set up for that purpose. So the sign convention here is, class, if you have a beam, if you cut here, and if we are using the free body diagram on the left hand side, so the Q is like this, pointing to the right, S is pointing downwards, M is counterclockwise as positive directions. If you are using the right hand side of the cut section, the free body diagram, so Q is pointing to the left as positive, S is pointing upwards as positive, and M is rotating clockwise as positive. So class, I would like to emphasize that this is the sign conventions for axial force, shear force, and bending moment. Do not confuse with the sign positive, negative that you can assume for moment at a particular point when you write down moment equilibrium equations. When you write down moment equilibrium equations at a particular point, you are free to choose clockwise negative or counterclockwise negative. That one is for summation of moment at a particular point. But here the sign convention here is for bending moment at a particular sections. And the next slides, I'm going to share with you, there is a meaning of this sign convention, the positive directions. Positive Q means if I cut here, so I get the Q appear. So if I use the left-hand side of the cut section here, the left-hand side, so the Q is pointing to the right. So when the Q is pointing to the right, so this is, remember, this force is the action on the other part. So the other part is pulling these sections. So the sign convention positive Q that we adopt here, meaning that we assume that particular section is in tension. We always assume first that particular section is in tension. So if you get Q If you assume as tension, if you get Q positive, let's say 20 kilonewton, meaning that that particular section is in tension. If you get negative, then that particular section is in compression. So that is for Q. And for shear force, if we take the left-hand side of the cut section, the free body diagram, our shear force positive direction is downwards. So if you look at this diagram, the meaning of the positive convention, the positive direction that we assume for shear force that we adopt here, it means that the external force tend to push. Now look at this. The external force tend to push the portion of the member to the left of the sections upwards relative to the portion on the right of the sections. So shear has this effect. Remember class, in what we have learned, shear effect, if there is a sliding, the tendency of sliding to happen at the sections. So positive shear means that we adopt means the phenomena is, if you look at this diagram here, it means that positive shear means the forces, whatever forces which is acting on this beam tends to push this part which is on the left side of the sections upwards relative to the right side here. So this is what happened. Positive Qs mean this section tends to be pulled in tension. So next, positive M has a meaning. Positive M has meaning, and positive N means these external forces causing positive bending moment, meaning that if I have a beam, so if the moment is positive, following the positive direction that we assume, meaning that the beam will bend upward like this. The beam will bend upwards at that particular sections. If it is the other way around, if the bending moment that we get is negative, which means it will bend downwards. Okay, so bend upward or bend downwards. So positive M here, if I use this left-hand side of the cut section, so the positive direction is as shown in this diagram here, class, counterclockwise. So the meaning of this positive bending moment is when the external forces or concentrated moment couples, it tends to bend the beam concave. Concave means it is upwards. It's like it concave upwards means the bending is like this. Concave upward, causing compression in the upper fiber and tension in the lower fibers of the beam. So it causes compression at the top, at the upper fiber, and correspondingly tension at the lower fiber, here. So this is compression at the top, tension at the lower fiber, compression at the top. That is for positive bending moment. So this is how we associate the positive direction that we assume for axial force, shear force, and bending moment to what happened at that sections. So positive Qs mean that section is in tension. Positive S mean at that sections, the left-hand side of that section tends to be pushed up relative to the right-hand side. And positive bending moment means that the beam will bend at that particular section concave upwards like this, causing compression at the top fiber and tension at the bottom fiber. This is for bending moment, class. It is important for you to take note when we go to one particular subtopic where you need to draw how the beam will bend under the loading acting on the beam based on bending moment diagram. So this convention is useful for you to remember when we want to draw how the beam will bend later on at the one particular subtopic that we are going to look at. So class, this is the sign convention that we adopt, okay? And it is important for you to remember the meaning of it. Okay? So shear force and bending moment of a section. So we discussed now mainly this is getting internal forces now. So for beam, we focus mainly on shear force and bending moment. Axial force normally does not happen in the beam, but axial force will become important when we have frame, because frame has vertical member, inclined member. That is when axial force tends to happen. So I show you here that basically when we want to determine shear force and bending moment, you need to do cuts. You need to know where to cut. Where are the sections where the bending moment and shear force are required. So we use this symbol like this, cuts, or we use a dotted line and we cut this, the beam will separate into two. So if you use the left hand side or right hand side, here I show the left hand side of the free body diagram, so I get the positive shear, positive bending moment. Axial force 0, I do not indicate here, but in general class there are 3. In this case, beam, the axial force 0. It doesn't mean they are not there, but the axial force 0, that's why it is not shown here. So location of the sections, you must be clear where the section is, and from there, from where you measure the sections. So location of the section, where is it? From this point, or from this point? Then shear force, we use S, sometimes we use V also interchange, okay? The important thing is understand that it is a force acting on this section parallel to that section. So once you have this free body diagram and once you determine the reaction force here, then you can get the bending moment and shear force using appropriate equilibrium equations. So this is what getting shear force and bending moment involves, the work. Know where the section where you want to determine the internal force, draw the appropriate free body diagram, either the part on the left or the part on the right, and then after that indicate correctly the shear force following our positive directions, following the sign conventions, and be clear about where the section is. Measure from where is the origin of that distance that the x coordinate, we call x coordinate, where we measure the section from. Then use equilibrium equations to determine the shear force and the bending moment. Okay, so now let me pause for a while then to see how many of you are currently joining the class now. Okay, let me show the taskbar. So we have now 87, okay, it's getting good. 87 still, it is not full. So class, I will pause for a while and then just